After we have explained the basic nomenclature of cable-stayed bridges, we now start to investigate the development of cable-stayed bridges from early beginnings until today. And we start, of course, with the precursors or forerunners of cable-stayed bridges. Today we treat the precursors which roughly can be classed from very early until World War II. All those were forerunners in various ways, and it started in earnest after World War II. So today we treat the forerunners until World War II. And since unknown times, people have built bridges across natural obstacles, rivers and so on, with natural materials. Famous are bamboo bridges, where lianen have been used as ties. And there are examples still today that local people build bridges like that. So the principle to support with some sort of a rope, either a vertical or a horizontal beam, is age-old, is a natural idea which you didn't need to study 5 years of engineering to come up with that idea. Also, ships, since men can think back, the masts of ships have been stayed at both sides with ties called shrouds, in German Wanten. And it is interesting to note that the French word for cable-stayed bridges, pont à aubin, goes back to that, because aubin are these ties, sidewards ties, Wanten in French. And the Russians, influenced from the French tradition, use cable-stayed bridges Wantowy most, Wantowy being the German Wanten. So these historical developments and early uses have partly been retained in different languages. What makes what we call a modern cable-stayed bridge? What are the essential characteristics? Because we will see now in the early development that some characteristics everywhere were missing, so it wasn't a real cable-stayed bridge. Well, basically all loads are directly transferred via forestay cables to backstay cables. Here at the anchorage, the vertical component, the turning over from here, is anchored downwards. I've shown you an example. And the horizontal component is taken in the beam. So the stay cables are anchored to the beam, not to the soil or somewhere. They are anchored to the beam, and the horizontal component from the backstay and the forestay, they equal one another out in the beam. So we have a system of ties here and compression member here. Of course, the tower acts in compression. And the main thing is then we have a hold down here, but the horizontal component is taken in the beam. That is the main system of a modern cable-stayed bridge. And you will be interested to hear that already in 1617, some people, in this case Faustus Verantius, by making a book, Machinae Novae de Fausti, also new machines by Faustus, where within many things, he sketched what we would call could call a cable-stayed bridge, a little bit reminiscent of a harp, a parallel arrangement of the stays. 100 years later, a German carpenter from Freiburg devised a timber stayed bridge with timber forestays and timber backstays as a possibility for a 70-meter stand. At the same time, the French engineer Poirier sketched various possibilities of bridges, including this type of cable-stayed bridge with a very clear fan arrangement of the stay cables. Now, all these and some others were not built. These were just some ideas in technical books. It all started, if one, as far as one knows history, the first, I call it nearly cable-stayed bridge, was built in 1817 in England, King's Meadow, where we have the main span stayed with cables like this. There's a backstay. Of course, there is no horizontal connection. This went somehow into the soil and this. But this stood up until 1922. This is a picture. Then it was taken down by a heavy flood and rebuilt and was active until 1950 when another flood took it down, and then it was built in another way. So, of course, a pedestrian, very light pedestrian bridge, but starting in 1817, sometimes similar. Then we had two failures of early cable-stayed bridges. There was we have here the second Dryburgh Abbey Bridge, and the first one was a suspension bridge with, it's a considerable span for that time, and that was so light that rather after 6 months after completion, the wind destroyed the pure suspension bridge, first Dryburgh Abbey Bridge across the Tweed River in Scotland. And so it was rebuilt, taking a big step, historically looked at. It was rebuilt by adding stay cables in the side, at the outer part of the main spans for stiffening the stay cables. It wasn't calculated or something, but it was by feel, and it worked. So, the second Dryburgh Abbey bridge is what I call early stiffened suspension bridge. Then came a very important example in Germany, which is hardly known. A French engineer friend, an American engineer with German roots, friend of mine, Charles Bernstein, dug that out and recalculated, investigated, published it, and so it came known again. Now, the Nienburg Bridge is in Thuringia across the Saale River. And it was one of the first examples which was rather close to the real thing, built in 1824 by somebody who wasn't really involved with bridges, with local artisans who'd never done a bridge like this. And it has a span of 82 meters, stay cables only. And here, again, it's not a real cable-stayed bridge because we have here the stays anchored to the soil, not to the beam, taking the horizontal forces. But it's coming rather close, and it's unique until today insofar that it has a bascule bridge in the center, and a Klappbrücke. There's a bascule bridge in the center. Here we see it. Actually, we are talking of two separate cable-stayed bridge, left and right, each with one tower, connected with a bascule bridge, which was to enable sail ships on the Saale River with high masts to sail through the bridge. Unique. Bandhauer was the name of the engineer, an excellent man, used all sorts of tricky details from his time, wrought iron, steel clamps and things like that. And there was a tragic outcome because the bridge worked very well. And it was even test loaded by a 6-ton horse-drawn cart. Work. And then, I think Christmas 1824, the Duke of Köthen, the Herzog, made a visit, and 300 people were on the bridge, and they were singing a song, and some tried to get the bridge moving, which you can do with a very light bridge, and the bridge fell down. They broke backstays, which were of bad quality iron at that time, and 55 persons drowned. So that was a major accident, was very much investigated, and it was shown the failure was due to bad quality of the wrought iron of the backstays. Bandhauer made a good design for his time. He was freed, but as a result, for about 125 years, no further cable-stayed bridges were built in Germany. From 1824 until early 50s, when it started in earnest. The French famous engineer Henri Navier investigated cable-stayed bridges as compared to suspension bridges. These were different bridge systems at his time, which he investigated, and these were his systems, still earth-anchored and so on. And he was, of course, a professor at the École Nationale des Ponts et Chaussées, which is still today the main school for bridge engineers in France, with all the famous bridge engineers teaching there. And he found, quite correctly, that contrary to a suspension bridge, which is basically only once statically indeterminate, if you cut the cable, you can calculate the forces in an approximation. A cable-stayed bridge, very roughly speaking, is as highly statically indeterminate as it has cables. So you very quickly come to 8, 10, 15 cables. They couldn't calculate it at that time. And he very clearly saw the direct load transfer of, if you put a load here, it goes directly in here and back here, as compared to the suspension bridge, where the bridge finds a new equilibrium without stressing the main cable, stressless deformations. But he said, we are not able to calculate the forces in a cable-stayed bridge, so we'd rather not build it. And that was the end of cable-stayed bridges for a considerable time in France also. Germany was the accident. In France it was Navier who said no good. So the development went on in England with the Twerton bridge, which used a rather stiff truss beam with stays which would also have been suitable for heavy railway loads, which otherwise have too much deflection. If one looks into it, and we come back to it in a further lecture, this is very close to what we call today extra dose cable-stayed bridges where loads are transferred partly by the stays and partly by the stiff beams. Now comes a hero, John Roebling, born Johann A. Roebling in Mühlhausen, Thüringen. Wenn Sie nach Mühlhausen gehen, I'm sorry, born in Mühlhausen, Thuringia. And if you go there at the marketplace, you find a plaque stating John Johann A. Roebling was born here. He studied engineering at the Polytechnicum in Berlin, but couldn't find really work, emigrated to the US with a group of people where they did farming first, and after some time he took up bridge engineering again. First built his own fabrication of ropes which he used for pulling ships, and then he started to build parallel wire cables in Trenton, Ohio. The manufactory was, until a few years ago, was still existing. And then he took up bridge engineering proper, stayed bridges with his type of ropes, and his great breakthrough was the construction of the Niagara Bridge in 1855. Now, that was the world record. We've forgotten to put the span on, I think something like 250 meters. And it had to serve railways. Now, I mentioned several times the high railway loads are a great problem for suspension bridges, because suspension bridges deflect too much so that the railway has to run up a hill too much, so they are not generally suitable. And what he used two methods to make this record span usable for railways. First of all, he used a very deep girder, timber truss about 8 meters deep. Now, when you stiffen the beam, of course, you reduce the deflection. It's not a typical suspension bridge, but it's stiffened by a stiff beam suspended. And secondly, he introduced stay cables in addition to the suspension bridge. Stay cables in something like the outer quarter, which again, as we know, due to the direct load transfer, stiffened the suspension bridge. And with these two measures, he was able to make this work as a railway bridge. Quite a breakthrough. And the invention, if you want to, of what I call stiffened suspension bridge. His great triumph, of course, was the Brooklyn Bridge in New York, world record at that time also, where again he used suspension system plus stays at the towers. You see it here. I don't know whether you've been there. You can cross today the Brooklyn Bridge as pedestrian, the elevated walkway, and you can have this view where we have the hangers of the suspension bridge and the stay cables in addition to stiffen. So I recommend highly to you, if you have an afternoon in New York, walk across the Brooklyn Bridge. Every taxi driver brings you to the tower, so it's worthwhile. It's very impressive. Roebling tried to design with his means the bridge by trying to distribute the dead load 1/2 into the stay cables. This is a drawing he made in his own hand, and there are the accompanying calculations, and the other half to go into the suspension catenary. In practical use, all these things lacked the possibility of determining the cable forces precisely on site. There were no hydraulic jacks, which you could stress a cable, measure its force, and of course the steel was very low in strength, and you've seen earlier the effective modulus of elasticity due to the sag was very low. So they were in our thinking not really effective, but they were effective enough to prevent wind oscillations and to help the use of railways. At the same time, Albert Bridge in London, you may know, one of the best maintained combination of suspension and cable stayed bridge. And then we have a new development in France with various engineers. The first was Ferdinand Arnaudin, who designed, who also had a fabrication of cables, wires first, and then started bridge designs. This was his first major Pont de Saint-Sulpice, the design, and that's how it looks today. It's still there, and it has been maintained. And he made here some good idea. He distinguished the area solely supported by stay cables, and the central part solely supported by the suspension hangers, which helped to understand a clearer flow of forces. He made several similar bridges the end of the 19th century, Saône River, Lyon. If you go down the National 7 to the south of France, you pass Lyon. So if you want to take a break, look at the bridge. This way of strengthening suspension bridges by adding stay cables is still used in exceptional cases today. There is a very famous Tamar Bridge in England. You may have seen these by Brunel. And this had to be widened. So it's a historic bridge, 150 years old. And the way it was widened was orthotropic decks were added to the side. This is the old bridge. Now it was widened by 2 lanes, and for these new lanes, stay cables have been introduced. One did not attempt to strengthen the original suspension cable, but added stay cables, of course, exactly calculated and exactly tuned, stressed on site. Now, there are a special type of bridges which were basically designed by Arnaudin in France, and these are called transporter bridges, in German Schwebefähren. If you wanted to cross a busy harbor for persons and goods, you could, of course, use a ferry, but the ferry hindered the ship traffic, and if in winter you have ice drift, you can't use them. So the idea was we build a high bridge, high enough to let the masts of the ship at that time pass. But that gets you easily to some 30 meters. And now to come down, if we go up to 6%, you need 500 meters to come down. No good. There was no space for that in the crowded harbor region. So what one said is, okay, we hang a gondola. I think it's in here. We can see it, another one. Here it is, yes. We hang a gondola at the level of the road and pull it over here when there is no ship in sight, and in winter it's free of the ice. So that's the basic idea of a transporter bridge. And now, to build these, Anodin first used his system of combination of suspension bridge with stays, all the horizontal component from suspension bridge and from the stays together tied back here with a long lever arm. Now, he came to the situation in Nantes, in France, that due to the build-up of the region, there was only about 25 meters which he could use as a backspan and no way to anchor things down here. And there he said, okay, now he used for the first time something which is very close to the modern cable-stayed bridge. You see, no suspension cable, but stay cables only, tied back here, and here we have a high up anchor or tie down pier, just cables running down into very, very massive anchor blocks from masonry. So this is one of the first, very close to the modern cable-stayed part in the transporter bridge at Nantes, 1903. There were nearly 20 of these major transporter bridges built at that time. We still have in Germany one across the Kiel Canal, unser Nordostseekanal. There is at Rendsburg is a Schwebefähre transporter bridge. So the road runs over it. If you go there, you can see it for pedestrians. Few are still existing. Now, what I call approaching the final form. We are now around 1900, and Anodin, with his transporter bridges, was already rather close. Appearing next, French engineer Albert Gisclar. Now, he developed his, in his company, he was a fabricator, contractor also, a bridge system, Gisclar, which was used widely in France, also in the French colonies, North Africa and so on, also for railway bridges. That again, at that time, it was the development of the railways at that time. And how you needed more bridges for railways than for roads, we know that because of the less grade accepted. And so, how to build bridges for railways? Now, in Saxony, where we are here, we know how to do. We built large stone arches, Göltztalbrücke, and all these beautiful structures, very massive and expensive. And so another way was looked into how to find a way to make these light suspended bridges suitable for railways. Well, one answer was make it as stayed as possible, and so System Gisclar was very welcome for railway bridges. The difference mainly to today are 2 points. He had his forestay cables not tied to the beam and anchored back in compression, but took it through in tension here and anchored it here at the other one, at the other abutment. Strange system for us, but that was the way. And also he had for the vertical components soil anchors, but it is in the principal idea close to cable stayed bridge. He had virtually no suspension bridge cables anymore, no hangers. It's coming close with these exceptions, and it worked, which is the main thing. Whatever some theoretical engineer says, it's no precisely this or that, it worked. And that, of course, is the main point. So he built many bridges. And the next famous French engineer, Monsieur Gaston Leinenkugel-Lecoq, was the son-in-law of Ferdinand Arnaudin, which we had heard before. And he also built, designed cable-stayed bridges very close to the final thing. We see it here, there is some overlapping and the cables run through here, tangent here, but it's close, and that's how it looks today. So he came, there was, by the way, one interesting point. Leinenkugel-Lecoq, as I say, was the son-in-law of Arnaudin. And when this Cassagne Bridge by Desclars was due to open, there was a test train running across, just a load test. And this railway derailed, and Desclars died in it, and Leinenkugel-Lecoq took a big jump, jumped out of the train in time, and he survived. So just as a little anecdote. So Leinenkugel-Lecoq put it further, the development, and so then we come to the eminent Spanish engineer, Eduardo Torroja, very well known as the father figure of the French engineers. They all refer back to him. And in our connection, he has done many outstanding things. In our connection, he stands out for his Tempoul aqueduct. Now, it's a small bridge, and it carries a water trough, einen Trog, an open cross-section for a water main across the river. And it was designed to have piers here and there. Now, when it came to build it, it came out no way to build reasonably piers here. Oh, good enough, he said, then we'll tie them back. And he used, for the first time, high-strength steel, meaning tendons for post-tensioning this part, and he then encased them in concrete. And the main thing which he did for the first time, after he had it built on scaffolding, he jacked up the tips of the tower. He had installed there from the cast in, so to say, hydraulic jacks, and had calculated precisely when I have this structure on scaffolding, and just as a homogeneous structure, take away the scaffolding, then I will get a certain sag and a stress distribution, which is not what I want. I want the stress distribution which would have been there if I would have had the two piers in the center. And to achieve those, he had to check up here and post-tension, however you call it, these stays, and by that tuning the bridge to the final situation he had calculated. That's what nobody had done before. There were no checks. They tried to stress the cable as good as possible, and good enough for bridge work was then probably the word, and that was it. But he calculated it precisely and knew what pressure oil pressure, jack pressure in his hydraulic jacks had to be, and he pumped the oil in until he had that pressure. So he knew the force in my cables is precisely that what I have calculated. And that was the first time, and that was basically the birth of modern cable-stayed bridges. It's still there, very small bridge. If you don't know the history, one would pass and wouldn't really look at it. But it has of great historical importance. Finally, the end of the precursors comes with Franz Dischinger. Now, he may have listened and taught in this very room because he made his PhD under Bayer. As you know, we are in the Bayerbau at Dresden University, then became professor at Berlin-Charlottenburg and one of the famous German engineers at the time. Now, he had the task to design a railway bridge across the Elbe River. Here we go again. I've told you half morning that that doesn't work. Well, he also found out that you cannot build a suspension bridge with, what was the span? Can you read it? Something 600 meters or so. I mean, across the Elbe River main span. And then he said, okay, and came back to old Röbling's ideas by distinguishing in the bridge different supports. In the middle, he still had a suspension support, but at the outside, he had a pure stay cable support. It came into the World War, was never built. However, in his publication, came out only in 1949. Yes, came out in here it says. In 1949, Hängebrücken für schwerste Lasten, suspension bridges for most heavy loads. It's in the library. If you have an hour, read it. It's very interesting because he put down on paper the main points of designing stays. He first of all came up with the effective modulus of elasticity. What I told you, the sag stress to the power of 3. Then he said, okay, we need high strength steel. We need to stress the cables on site to the desired force, because then we can calculate the support conditions in the final bridge. So the basic ideas, especially for the stay cables, are all in his 1949 publication, and was read at that time by many engineers. And of course, Germany was, 1949, completely in ruins. There was no Rhine River bridge in existence. And all these Rhine River bridges, which are the longest bridges in Germany, it's a pity we need only 300 meters main span. That's what it is. We don't need more than across the Rhine River. But so the engineers had to think, what about with a shortage of material at that time, no steel proper and so on. And that was in a situation then, Germany in need of a economic bridge system, that these ideas were taken up, especially then, we will see in the next lecture, Düsseldorf first, Düsseldorf Bridge family, Strömsund, and so on. And the first proper cable-stayed bridges were then designed immediately after this, following this publication, and then spread all over the world. So, this is what I wanted to tell you about the precursors. It's not that you have to learn it by heart. but I think one should know the historical development if one discusses things in detail today. Where did it come from, and how was the development in, not in circles, but deviating left and right until we arrived where we basically are today. Thank you very much.